Good morning, everyone. We're going to get started on Unit 2 today. Unit 2 is called Forces and Fields, and we're going to spend about half of the unit dealing with what are called electric forces and fields, and the other half of the unit talking about magnetic forces and fields. We're going to be looking today at starting with lesson 2.2, and that's called Coulomb's law. We're skipping over the first lesson because the first lesson is taught using a large number of demonstrations. There are a lot of conceptual ideas that are difficult to wrap our heads around in the first lesson unless we have some visual demonstrations to explain some very important concepts. Without me being there, it's just not going to translate well in terms of a video. So when I get back next week, I will go through all of those demonstrations and we will cover that lesson at that time. So today we're going to be looking at Coulomb's law. A few objectives here. First of all, we're going to understand the similarities and differences between what's called the universal law of gravitation, which you learned about last year in Physics 20, and I will review with you this year, and the law of electrical interaction, also known as Coulomb's law. Both of those laws, universal law of gravitation and the universal law of electrical interaction, or Coulomb's law, they both follow what's called the inverse square law, so we're going to have to review what that is. You do learn about the inverse square law in Physics 20. And then we're going to be solving some problems using Coulomb's law. Coulomb's law, there's a bit more to it than this, but what it boils down to basically for Coulomb's law is it's a formula which allows you to calculate electrical forces between what we call charged objects. Before we actually get into any physics, I need to review with you some fundamental ideas in math. And these ideas that I'm going to review with you here are not being reviewed just so that you can understand Coulomb's law. They're being reviewed because there's a type of analysis that we do in physics, and we're going to have a lesson on it next week. It's called graphical analysis, and your understanding of graphical analysis is tied very closely to what I'm going to talk about here when I review proportionality. What does it mean when I say two variables are directly proportional to each other? Well, first of all, we write it that way. We say y is proportional to x. So when you see this statement, we're just saying that y and x are proportional to each other. Now, what does that mean? Well, it means that as one of the variables basically increases, the other increases by the same factor. So, for example, if I talk about the amount of liters of fuel I pump into a vehicle at a gas station and the amount of money that I charge the people for the fuel, those two things are directly proportional. If you want twice as much fuel, you're going to pay twice as much money. And graphically, what that translates to is this type of graph. A direct proportionality is what we also call a linear relation that goes through the origin. So this is what a proportionality means. If y is directly proportional to x, then this is what the graph looks like. But the statement y is proportional to x can be used to create an equation by finding what we call a constant of proportionality. And it turns out that the constant of proportionality is equal to the slope of the line. I mean, going back for a second to this graph, you should know that the equation of a line that's a straight line, generally speaking, is y equals mx plus b, but looking at this graph, b is 0, b being the y-intercept, which means the equation of this line is y equals m times x. So when y is proportional to x, y is equal to m times x. And all I'm telling you here is that that constant of proportionality in terms of a science approach is really the mathematical slope of the line. So the equation relating the two variables that are proportional to each other is that the vertical variable is equal to that constant of proportionality times the horizontal variable. And if you think of my analogy of how many liters of gas I pump and how much I charge my customer, how much I charge the customer would be y, x would be how many liters there are, the constant of proportionality would just be something like $1.43 because it's $1.43 per liter. So let's do an example here that's not a physics example, it's a math example. It says a group of elementary school students are given 8 balloons and 8 different values of diameters. They're instructed to inflate the balloons to each of the diameters and measure the resulting circumferences and then plot the circumference compared to the diameter. And they create a nice graph. I would imagine that if you actually got elementary school students to do this, their graph would probably be all over the place. But assuming that they're perfectly measured and these balloons are perfectly spherical, they get this graph. And it says determine the equation relating the diameter to the circumference. Well, looking at this, you can see that the circumference is directly proportional to the diameter. And that means that the circumference is equal to the constant of proportionality, which is the slope, times the diameter. And in order for us to find the slope, it's really not that difficult. We have the coordinates of 2 pairs of points here. What you need to do is find the rise and find the run and divide them. So the rise would be the y coordinate minus the y coordinate, which would be 54.6 minus 18.2. And this is divided by the run. The run would be 17.4 minus 5.8. Again, you might be looking at this thinking, what does this have to do with Physics 30? The answer is a lot. It has a lot to do with Physics 30. It has a lot to do with scientific analysis. So if I take 54.6 and subtract the 18.2, that's the top of my fraction. I shouldn't say fraction. We want a decimal. I want to divide that by whatever 17.4 minus 5.8 is, and I get a slope of 3.14. So my answer is that the slope is 3.14, which means the equation in this little experiment is circumference equals 3.14 times diameter. It shouldn't be lost on you that 3.14 is pi, and that equation makes sense. Circumference is found by multiplying diameter by pi. Now let's get to the physics, and I'm going to back up here, and for probably the next 10-15 minutes approximately, I'm going to be reviewing what you learn about gravitational forces and Isaac Newton's universal law of gravitation. I'm going to be reviewing all of that from Physics 20. But at the same time, I'm going to be ramping up my explanations a bit to a Physics 30 level. So I want to talk about the problem of what we call gravitational force and what Newton came up with for an idea. The problem of gravitational force is basically we know that any two masses in the universe, and I have them listed up here as M1, M2, we know that any two masses in the universe are attracted due to what we call the force of gravity. Force of gravity is really a mysterious thing, but we're not going to talk today about explaining why gravitational forces exist. What we want to know is, what's the relationship between all of these things? These two masses are both pulled together with what we call the force of gravity. And it makes sense that the force of gravity must be related in some way. That force of gravity must be related in some way to the mass of each object and to how far apart they are. And Isaac Newton came up with a hypothesis. A hypothesis is a general prediction. And his hypothesis had to do with proportionalities. And what he proposed was that the gravitational force was directly proportional to the two masses. And I want to talk about this. I don't want to just hand wave this away as if it's not important. The gravitational force is proportional to the product of the two masses. What does that mean? It means that if you measure the gravitational force between two masses, and then you take one of the masses and make it 5 times larger, then the gravitational force will be 5 times greater. So as an illustration here, and you can choose to write this down in the margin of your notes or on a piece of paper if you like. If we had a gravitational force between two masses and the magnitude of that force was 100 newtons, and one of the masses was 10 kilograms and the other mass was 4 kilograms, and what we did was we kept those two masses at the same distance, but we took the first mass and we did this to it. We changed it to 30 kilograms, and we took the second mass and we changed it to 2 kilograms. Then what I've done is I've multiplied one of the masses by 3, and I've multiplied one of the masses by 1/2. That highlighted part is telling you the new gravitational force can be found by multiplying the old gravitational force by 3 and the old gravitational force by 1/2. And I'll leave it to you to figure out that what you're going to get there is 150 newtons. Essentially, everybody, what I have highlighted in yellow is saying whatever happens to the mass happens to the gravitational force between the masses. That's the first part of his proposition. The second part of his proposition is a little bit more complicated. So I've talked about the yellow part. Now I want to highlight, I'll use green. The second part is that the gravitational force is inversely proportional to the square of the distance. And I hope you can appreciate, looking back at the problem at the top of this page, that r is what we use for the distance between the masses. So what Isaac Newton is saying, and I'm going to need to explain this to you, is that he believes that the gravitational force is inversely proportional to the square of the distance between the bodies. So there's two parts to that inverse proportionality. First of all, inverse. In this context, what it means is that if the distance between the bodies gets bigger, the force gets smaller. See, with the relationship between the force and the mass, which is what's highlighted in yellow, as the masses increase, so does the force. The inverse proportionality with regards to distance means as the distance gets bigger, the force gets smaller. Or, as the distance gets smaller, the force gets bigger. Listen, intuitively, I think that makes sense. I think you can appreciate that two masses that are closer together experience a greater force of gravity. But what about the square part? Well, that means that whatever happens to the distance, the opposite, because it's the inverse proportionality, the opposite of the square happens to the force. If we started off with 100 newtons, and instead we went from r equals 3 meters, and we went to r equals 1 meter, then what you're doing to that distance is you're dividing by 3. So what would you do to the force of 100 newtons? Well, it's an inverse square. So the inverse of dividing by 3 is multiplying by 3, but it's multiplying by 3 squared. So you would have to take 100 times 3 squared, which would give you 900 newtons. Those two proportionalities are true. then it turns out that the gravitational force is proportional to m times m over r squared. If F is proportional to m times m, and F is proportional to 1 over r squared, then F must be proportional to mm over r squared, putting them together. What that means is there has to be a constant of proportionality that makes those things into an equation. If Fg is proportional to this mess, then y equals some constant of proportionality called the slope, if you want, multiplied by that thing. So we're going from a proportionality statement to an equation. And the person who did that was a guy by the name of Cavendish. Cavendish proved Isaac Newton's hypothesis true. And he did it using what's called a torsion balance. If you've ever seen this experiment, you would probably see it in university. You can see videos on YouTube of it. You have a metal bar, and attached to the bar are two spheres of lead. They're really quite massive, and they're hanging balanced by a very, very thin wire. Those two spheres that you see there are equal in size. They just appear differently sized because one is further away from you. And what Cavendish does is he brings another mass close to one of the masses. So M2 is brought close to M1. M1 is one of the two masses in balance. And what he observes, and if you get a chance to see this, it's really spooky, is that that whole thing rotates. It's massive, but there's a gravitational force of attraction big enough to twist that wire. And M1 and M2 will be pulled together. And they're pulled together because of the force of gravity. By the way, if you measure the angle of the twist, you can figure out how many newtons of force are twisting it. So what Cavendish is able to do is measure M1 and M2 and measure the force between them. He can also measure the distance between them by looking at this apparatus. And what he discovers is that when he makes a graph of Fg compared to M1, M2 over r squared, if Newton is right in his hypothesis, if these two things are proportional, then you should get a straight line, and Cavendish gets a straight line. All of his data falls in a straight line. And what Cavendish now does is he finds the slope of the line, because the slope is the constant of proportionality. And he discovers that the slope has a value of 6.67 multiplied by 10 to the negative 11. The units happen to be newtons times meters squared over kilograms squared, and I'm just going to ignore explaining today. Don't worry about it. I will explain it in more detail when I return. But those are the sets of units. And that constant is called the universal gravitational constant, which is on your formula sheet. Okay, so what? Well, this is the bottom line. Between Newton and Cavendish, they've created a law of gravity. It's called the universal law of gravitation, which you can use to calculate the gravitational force between any two masses in the universe. And, you know, if I were there, I would look everybody in the eyes and say, do you remember seeing this last year? And everybody would say yes. Now, what is the problem of electrical force? What I'm about to do is go through the exact same thing I went through with the gravitational force problem, but I'm going to go quicker. First of all, what you would have learned in the first lesson, but it hasn't been taught to you yet, and I feel as though I want to write this down, is that gravitational forces need mass. I will often say in this class that mass is the property of matter responsible for gravity. You cannot have gravity unless you have mass. Electric forces, we use the symbol lower e for electric here. Electric forces need charge. There is a property of matter called charge. Not all pieces of matter have charge. Electrons have charge, protons have charge, neutrons do not have charge. A balloon that I blow up and put on the counter does not have charge unless I take that balloon and rub it through my hair. Then when I put the balloon on the counter, it does have charge. So what is the problem of electrical force? Since charge is responsible for electric force, and I need to back up and show you one more thing, the symbol for mass is m, we use the symbol Q for charge. So the problem of electric force is when you have two charged objects where the charge on one is Q1, the charge on the other is Q2, and they are, in this case, attracted by an electric force because they're a certain distance apart. What's the relationship between everything here? And again, I have to explain something that you're missing because we didn't do the first lesson. Electrical forces can be attractive or repulsive. Very briefly, if you have a positively charged object next to a positively charged object, they will repel. Similarly charged objects repel. Whereas if you have a negatively charged object next to a positively charged object, they will attract. So the question is, how do you calculate the force? Well, Priestley basically looked at Isaac Newton and copied him. This is, I want to say 100 years later, but maybe it's not quite 100 years later. Since Newton believed that gravitational forces were inversely proportional to the square of the distance, Priestley believed electric forces were. Since Newton believed that the gravitational force was directly proportional to the product of the masses, and mass gives rise to gravity, Priestley says, well, I believe the electric force is directly proportional to the charges. And when you put those together, you get that proportionality statement. And that means that there must be some constant of proportionality, that if you multiply that constant of proportionality by Q1, Q2 over R squared, you'll get F. To show this to you in a different way, and this analysis or this comparison of the equation in physics to the mathematical statement of y equals mx is crucial later on in this unit. Y equals the slope times x. Y equals the slope times x. What this is saying is if you plot a graph of the electric force as a function of Q1, Q2 over R squared, the slope of that line will be the constant of proportionality. And maybe more important to everybody, if Priestley's right, you get a straight line. Coulomb is the person who proved Priestley right. And what Coulomb did is he basically copied Newton as well. He did a torsion balance experiment, except instead of using masses, he used known charges. So we've got two spheres that carry a charge. Well, one of them is charged, but it's balanced. That charge is Q1. A second charge is brought in the vicinity of that, and then the torsion balance twists. In this case, Q1 moves away from Q2, telling Coulomb that the two charges are similar. But again, based on how much twist there is, the electrical force can be measured. So Coulomb's measuring all these things. He measures Q1, he measures Q2, he measures the force, he measures the distance between the spheres, and he plots a graph. And sure enough, the graph is a straight line. And just like Cavendish, Priestley finds the slope. And the slope happens to be 8.99 times 10 to the 9. And again, I'm not really worried about the units today. That constant is called Coulomb's constant. It's given a symbol of K. So now we have a similar formula for electrical force. It's similar to the one we have for gravitational force. And I need you to get out your formula sheet now so we can refamiliarize ourselves with where Newton's universal law of gravitation is and also where this new law is. When you go to your formula sheet under dynamics, you find Newton's universal law of gravitation, and under electricity and magnetism, you find Coulomb's law. The constants, capital G is what we use for the constant of proportionality for Newton's law, is under the constant section. It's called the gravitational constant. And the one I've got circled in blue is Coulomb's constant, 8.99 times 10 to the 9 Newton meter squared per Coulomb squared. So there's one other thing that I have to talk about now. I just realized mass is required for gravitational force, charge is required for electric force. The units of mass are kilograms. The units of charge are called coulombs. So when you look at your formula sheet at Coulomb's law constant, and it has units of Newton meter squared over c squared, that's over Coulomb squared. All right, now we're going to get to work. So you need your calculators out. Example 1 says compare the gravitational attraction with the electrical force of attraction between an electron and a proton in a hydrogen atom if they are 5.29 times 10 to the negative 11 meters apart. So as I write this stuff on the board, I'm not going to put units because I don't want to make a big deal of it today, but the gravitational force using this formula will be capital G, which is 6.67 times 10 to the negative 11, and it has units, but I'm not worried about it today. And now I have to multiply by the mass of the electron and also by the mass of the proton. We have these two things which are this distance apart. And if you go to your formula sheet, you're going to become very familiar with these numbers, but when you go to your formula sheet, there's a section on the constant side that's called particles, and you can see what the mass of an electron is. The mass of an electron is 9.11 times 10 to the negative 31 kilograms, and you can see what the mass of a proton is. It's hard to imagine, but there will be a time in this course where you will just know those numbers. So I'm going to go ahead and put them in. The mass of an electron is 9.11 times 10 to the negative 31 kilograms. The mass of a proton is 1.67 times 10 to the negative 27 kilograms. There will be a time in this course as well where we learn how we know those masses. We're going to learn about the experiments that were performed about 120 years ago to determine some of these pieces of information. And then we divide by the distance squared, which is 5.29 times 10 to the negative 11. And we have to square that. We can go ahead and calculate that. 6.67 times 10 to the negative 11 multiplied by the mass of the proton. When you're using scientific notation, please use the E function on your calculator. Don't type multiplied by 10 raised to. Just use that. I also have to multiply by the mass of the proton. And then I have to divide by 5.29 times 10 to the negative 11. And I need to square that. There is no need to put any of this in brackets. I'm double checking. I'm just standing here double checking what I've typed. Looks okay. I get about 3.6 times 10 to the negative 47 newtons, a very, very tiny gravitational force. Now what we have to do is calculate the electric force between those two. Well, we have a formula. It's KQQ over R squared. So I'm going to take K. I look at my formula sheet, and Coulomb's constant is 8.99 times 10 to the 9. I'm going to multiply that by the charge of an electron and the charge of a proton. Well, just a second. Let's go back and take a look here at the formula sheet. What's interesting here is it doesn't really tell you the charge. Let me explain. It tells you that the charge of an electron is negative 1e and the charge of a proton is positive 1e. And that's not really telling you anything. However, E is an abbreviation for what's called the elementary charge. And when you look at the constants section of your formula sheet, you can see that the elementary charge is 1.60 times 10 to the negative 19. And what that means, everybody, is that the charge of an electron is negative 1 multiplied by that elementary charge, and the charge of a proton is positive 1 multiplied by that elementary charge. In other words, the charge of an electron and the charge of a proton are the same amount, but they're oppositely charged. And I think even without going through lesson 1, everybody understands that charge comes in two types, positive and negative. It's why electric forces can be attractive or repulsive. Whereas mass comes only in one flavor or one type, mass. There's no positive or negative mass. It's all mass, which is why gravitational forces are always only attractive. They can never be repulsive. All right. Now, the only other thing I want to point out to you is that the charge of an electron is negative 1.6 times 10 to the negative 19 coulombs. However, when you use this formula, you never put negatives in for the charge. So for the charge of an electron, we're just going to go 1.6 times 10 to the negative 19 coulombs, and then 1.6 times 10 to the negative 19 coulombs. And then we're going to divide by the 5.29 times 10 to the negative 11. Don't forget to square it. I did the calculation with you for the gravitational force. What I would like you to do now on your own is calculate what the electric force is equal to. And I'll give you a minute to come up with a number. I believe it's 8.2 times 10 to the negative 8, and what I'm going to do is just double check that. Here's my Coulomb's constant. I'm going to multiply by the charge of an electron, and I'm also going to multiply by the charge of a proton. Since those two numbers are the same, when I enter it in my calculator, I can just say squared. Now divided by 5.29 times 10 to the negative 11. And there's a common mistake. I forgot to square So I get 8.28 times 10 to the negative 8. Now, let's look at those two numbers. I've got them down here. Those are the two forces. And if I were to ask you, are either of those two forces significant, your gut reaction would probably be to say, no, they're both minuscule. However, I want to point out to you that when you're asked to compare things in science, it's better always to divide. So if I divide the larger of those forces, which is 8.2 times 10 to the negative 8, and I divide that by the smaller, which is 3.6 times 10 to the negative 47, I get this number. I get basically 10 to the 39. I'm telling you that in an atom, the electrical force between the particles is 10 to the 39 times greater than the gravitational force. All right, example 2 asks you to find the acceleration of the electron. Well, F net equals ma. And when you take a look at the two forces acting on the electron, you need to add those two forces together to get the net force. But when you add them together, all you're going to be getting is the electric force. You can feel free on your calculator to take that, go back and look at the numbers, to take 3.6 times 10 to the negative 47 newtons and add it to 8.2 times 10 to the negative 8 newtons. But when you add them, you will get 8.2 times 10 to the negative 8. Because that 3.6 times 10 to the negative 47 is so tiny. So essentially what I'm saying is, in an atom, gravity is not significant. So in our F equals ma, we're going to use the net force as being the electric force. The mass of the electron is 9.11 times 10 to the negative 31. And this will give us the acceleration. It's going to be a centripetal acceleration because in an atom, electrons move in a circle. And that's not important for this question. What is important is the answer. When you take that 8.2 times 10 to the negative 8, I don't care about all the digits, and you divide by the mass of the electron, you get a staggeringly large acceleration. You get 9 times 10 to the 22 meters per second squared. And I'm mentioning that because you may have looked at the force, this is your eyeball, you may have looked at that force and said, there's nothing there. There is something there. It's a huge force acting on that electron because of what it does to the electron. It causes the electron to accelerate at an insane value. Number 3, determine the net electrical force on the middle charge due to the other two charges. What I would like you to do is I would like you to label these spheres as A, B, C from left to right. And let's talk about a couple of things here. First of all, net means total. And then we also need to talk about this symbol in front of the Coulomb sign in all of these charges. If you go to your formula sheet, there's a section on your formula sheet with the metric prefixes, the prefixes that we use in the SI system. And this is the Greek letter mu. And in the context of seeing it in front of a unit, it means multiplied by 10 to the negative 6. So that 15 microcoulombs, it's called micro, by the way, that's the way we pronounce it, is 15 times 10 to the negative 6 coulombs. The 10 microcoulombs is 10 times 10 to the negative 6. Now, let's get back to the question. You were asked to determine the net electrical force on the middle charge. So take a look at the charge in the middle and the charge on the left. Take a look at charges A and B. They are oppositely charged. A is positive and B is negative. That means that B will be attracted to A. It's going to be pulled towards A. Now look at the charge B and the charge C. They are both similarly charged, and that means that B is going to be pushed away from C. So the middle charge is attracted to the left because the left charge is opposite to the middle charge. The middle charge is repelled from the right because the right charge is similarly charged to the middle charge. These two forces that I've drawn are what we can call Coulomb forces. I'm not going to write a lot for this question, but I am going to just write to begin with here that the amount of electrical force between A and B will be equal to K times QA times QB over the distance squared. And the amount of electrical force between B and C will be equal to K times QB times QC over that distance squared. You should be familiar with these types of questions from Physics 20 where you did them with masses. The bottom line is you have the tools necessary to calculate the electric force between A and B using Coulomb's law and the electric force between B and C using Coulomb's law. I'm not going to bother writing in all of the numbers. If you follow along with me on my calculator, when I want to find the electrical force between A and B, I can take Coulomb's constant, multiply by the charge of A, which is 10 microcoulombs. So look very carefully. I'm going to clear my calculator screen so you can see it better. I'm taking Coulomb's constant. I'm multiplying by 10 microcoulombs. So look at what I've entered there. I'm multiplying by 10 times 10 to the negative 6. I also need to multiply by 15 microcoulombs, which is 15 times 10 to the negative 6. I don't put the negative in with the 15 though. And then I need to divide by that distance in meters squared, which is 0.016 squared. This is the force I get for the force between A and B. If I repeat the process now, I can find the force between B and C. I'm going to take Coulomb's constant. I'm going to multiply by the charge of B, which is 15 microcoulombs. I'm going to multiply by the charge of C, which is 45 microcoulombs. And I'm going to divide by the distance between B and C in meters squared. So I've got my K, Q, Q over R squared. And what I get for that force, obviously entered something wrong here. My 9 didn't stick on Coulomb's constant. So K, Q, Q over R squared. What I get is this number. And now what we can do is say that this 5267 newtons, this is newtons left. Because once again, we were talking about the force between A and B are oppositely charged. So which way is B forced? We're finding the force on B. It's forced towards A, which is to the left. This is 5249 newtons. It also is to the left. Why is it to the left as well? Well, because B and C are similarly charged. So when you talk about the direction of the force on B, which is what we're asked about, B will be pushed away from C. And what you're left here with is adding two vectors. But those vectors are in the same direction, which means the answer to our question is simply going to be that first force of 5267.578125, if you want to carry all your decimals, added to the second force which gives me 1.1 times 10 to the 4 newtons to the left. And that's the answer to that example. Let's take a look at number 4. The force of repulsion between two charged spheres is 2,200 newtons. What happens if you double the charge on one sphere and triple the charge on the other? Well, the electric force is proportional to the product of the charges. This goes back to the very beginning. Whatever happens to one of the charges has to happen to the force. So if I double one of the charges, the force will double. If I triple the other charge, the force will triple. The bottom line is if we take that 2,200 newtons and multiply it by 2 and multiply it by 3, we are going to get the answer. Well, 2 times 3 is 6, so I'm just going to multiply by 6, and you get 13,200 newtons. What if the distance between the spheres is tripled? Well, going back to the beginning, I told you that an inverse squared proportionality means that whatever happens to the distance, the opposite of the square happens to the force. So if we have 2,200 newtons, and I'm multiplying the distance by 3, that means I'm going to divide the force by 3, but it's an inverse squared relationship, so I have to divide by 3 squared. Which is 9. So I get about 244 newtons. We can put this all together. Look, if the charge on each sphere is doubled, then what that's going to do is take the force and multiply by 2 and multiply by 2. If the distance between the spheres is reduced to a quarter, that means I'm dividing the distance by 4. That means the opposite of dividing by 4 is multiplying, and I have to do it squared. This is how you would find the new force. So 2,200 multiplied by 4, that's the 2 times the 2. I'll do it this way, I don't want to confuse you. And then times 4 squared, which is 16. So you get 1.4 times 10 to the 5 newtons. I'll be honest with you, my head is a little cloudy right now, so I've lost track of the time, but I'm going to end it there. I'm not going to worry about the final example. I will either include it in the next video lesson, or we will talk about it when I return. So 5 and 6 are out. I'm going to ask you to get started now on 1 to 13 on pages 13 and 14 of the handout, and Mr. Gertson will tell you what I've decided should be done for the next class. I hope that went okay. As I said, my head is not exactly clear right now, and I have a feeling I may have gone a little long, but that's okay. We can make up the time later. In the meantime, have a great rest of the day, everyone, and a great evening, and I hope to talk to you soon. Take care.